Let me start. Today we will discuss about the magnetostatics. We have already known that steady current produces magnetic field. The magnetic effect of steady current is known as magnetostatics. Suppose a charged particle of charge q moves with a velocity v in presence of magnetic field B. Due to the presence of magnetic field, the force acting on the charged particle is equal to force F m is equal to q into v cross b. V cross b. The direction of the force is both perpendicular to the velocity and the magnetic field. This force is known as magnetic force. Sometimes it is called Lorentz force. Due to the magnetic force, suppose the charged particle q moves in a distance dr. Due to displacement of the charged particle, the charged particle some work W is equal to force into displacement, force Fm dot dr. This is the work done. So, force equal to q into v cross b dot dr, where dr is the displacement of the charged particle due to the magnetic field. We know that the displacement dr, the rate of displacement with respect to time is equal to v. Rate of change of displacement is equal to velocity. So, dr is equal to v dt. Now, replacing the dr, we get the work done W is equal to q v cross b dot v dt. Now, using the vector identity A dot B cross C is equal to B dot C cross A is equal to C dot A cross B. So, we can write the work done q v cross v dot b into dt. So, v cross v, the cross product of same vector is equal to 0. This implies that the magnetic force do not any work. Suppose this is equation number 1. Also, according to the work energy theorem, the work done W can be written as W is equal to change in kinetic energy T2 minus T1. According to work energy theorem, the work done is equal to change in kinetic energy, where T2 is the final kinetic energy of the particle and T1 is the initial kinetic energy of the particle. Suppose this is equation number 2. So, comparing equation 1 and 2, we can write T2 minus T1 is equal to 0. So, T2 is equal to T1. T2 is equal to T1. This means that the magnetic force do not change the kinetic energy of the charged particle. In addition of external electric field, the force acting on the charged particle is equal to Fe, that is equal to charge into electric field. In addition of external electric field, the force acting on the charged particle is equal to charge into electric field. And so the total force acting on the charged particle due to electromagnetic field, that is force due to electric field, force due to electric field plus force due to magnetic field. This is the total force acting on the charged particle. This force is equal to Q E plus Q into V cross B, that is equal to Q into E plus V cross B, V cross B. This force is known as Lorentz force. Lorentz force. Now we have to calculate the force on a current carrying conductor. Force on a current carrying conductor. Force on a current carrying conductor. We consider a elementary length of conductor. We consider a elementary length dl carrying a current I along its length. Suppose A is the cross section area. A is the cross section area of the conductor. Let n be the number of charge per unit volume. So the volume of the elementary conductor is equal to cross section area into length. Volume of the elementary conductor is equal to cross section area into length. So the charge contained within this elementary conductor, is equal to Na dl. We have already known that the force acting on the charge Q is equal to force acting on the charged particle Q is equal to Q into V cross B. So the total force on the elementary conductor, is equal to Na dl Q into V cross B. Since the velocity of the charged particle is parallel to the length, so we can write the force on the elementary conductor is equal to Na Q V dl cross V. This quantity Na Q V gives the current. So dF is equal to I dl cross B, where B is the magnetic field, apply on the conductor. If the conductor have a finite length, so the total force acting on the finite length of the conductor can be written as F equal to I dl cross B integration. The force acting on the finite length of conductor is equal to I dl cross B. If the conductor or circular loop placed in a uniform magnetic field, then the force acting on the closed loop can be written as F is equal to closed integration of I dl cross B I dl cross B. if the magnetic field B is uniform, then the force on the elementary conductor I B close integration of dl. Since the close integration of dl is equal to 0, so that is equal to 0. So, force acting on a closed loop placed in a uniform magnetic field is equal to 0. Next, we discuss the Biot-Savart law. We have already known that steady current produce magnetic field. Ampere perform a series of experiments, and from the experimental result a definite law came out, and this law determined the magnetic field produced due to the current. This is known as Biot-Savart law. Suppose we consider a current carrying conductor carrying a current I. We consider an elementary length dl on the conductor. Suppose the position vector of the elementary length with respect to some arbitrary origin O is equal to r prime, and the position vector of the elementary length with respect to origin is equal to x prime, y prime, z prime. And we consider a point P. The position vector of the point P with respect to origin is equal to, this is r prime, this is r, and the position vector of the point with respect to elementary length dl, that is r, capital R, is equal to r minus r prime according to vector triangle law. According to vector triangle law, capital R is equal to r minus r prime. So, this point P is known as field point, and the elementary length dl, this point is known as source point. Now, according to Biot-Savart law, the magnetic field at point P due to the elementary length dl can be written as dB, that is equal to mu 0 by 4 pi I dl cross r by r cube. Mu 0 by 4 pi I dl cross r by r cube, where mu 0 is equal to 4 pi into 10 to the power minus 7 Newton, 4 pi into 10 to the power minus 7 Newton per ampere square. This is called free space permeability. So, the total magnetic field at point P due to the entire conductor can be written as, according to superposition principle, total magnetic field at point P due to the entire conductor is equal to mu 0 I by 4 pi integration dl cross r by r cube. Suppose this is equation number 1. If instead of line current distribution of charge, if we consider a volume current distribution of charge, that is, we consider an elementary volume dV prime, the position of the elementary volume with respect to origin is r prime, and the position of the point P x, y, z, that is equal to r. So, the position of the point P with respect to elementary volume capital R is equal to r minus r prime. For volume current distribution of charge, IDL, current into dl, length, IDL can be written as I is the current density, J n hat ds into dl. So, this is equal to J dV. So, in terms of current density, the magnetic field for volume current distribution of charge is equal to B mu 0 by 4 pi integration J cross R by R cube into dV. Suppose this is equation number 2. So, equation 1 and 2 is known as Biot-Savart law. This equation for line current distribution of charge, and this equation is the volume current distribution of charge. This integration is taken over the volume. These two equations are known as Biot-Savart law. Next, we discuss about the application of Biot-Savart law. First application of Biot-Savart law is long state current carrying conductor. Long state current carrying conductor we consider a long state wire AB carrying a current I. Due to the flow of current, we have to calculate the magnetic field outside the conductor. Suppose we have calculated the magnetic field at point P. The distance of the point P from the axis of the conductor is equal to A. We consider an elementary length dl at a distance L from the origin O. Origin, or this point is the foot of perpendicular from the point P. Now, this is R, capital R. Suppose the angle between capital R and dl is phi. This angle is theta. So, according to Biot-Savart law, the magnetic field produced at point P due to the elementary length dl is equal to dV, that is equal to mu 0 I by 4 pi dl cross R by R cube. dl cross R by R cube. So, the total magnetic field at point P due to the entire conductor is equal to integration of mu 0 I by 4 pi integration of dl cross R by r cube. Now we have to calculate this quantity. Now from figure, dl cross r by r, dl mod of dl cross r gives dl and r, dl r sine angle between dl and r, that is sine phi. Mod of dl cross r is equal to mod of dl mod of r into angle between r and dl. So this quantity is equal to dl r sine phi is equal to, this angle is equal to 90 degree plus theta, 90 degree plus theta, that is sine 90 plus theta. dl r cos theta, sine 90 degree plus theta gives dl r cos theta, and L by A is equal to tan theta, or L is equal to A tan theta. So dl is equal to A sec square theta d theta, dl is equal to A sec square theta d theta, and r by A is equal to sec theta, or r is equal to A sec theta. So replacing this quantity, we get the magnetic field. Due to the entire conductor is equal to mu 0 I by 4 pi integration cos theta d theta. Limit of the integration is minus theta 1 to theta 2, where theta 1 and theta 2 are the angle, theta 1 and theta 2 gives the angle of the end point of the conductor. So total magnetic field B is equal to mu 0 I by 4 pi. This integration is equal to cos theta integration sin theta, limit minus theta 1 to theta 2, that is equal to mu 0 I by 4 pi sin theta 2 plus sin theta 1, mu 0 I by 4 pi sin theta 2 plus sin theta 1. If the length of the conductor is infinite, if L is tends to infinite, then theta 1 and theta 2 is nearly equal to pi by 2. Theta 1 and theta 2 is nearly equal to pi by 2. So total magnetic field for infinite length of conductor B is equal to mu 0 by 4 pi sin 90 degree plus sin 90 degree. Sin 90 degree is equal to 1. So mu 0 I by 4 pi 1 plus 1. Mu 0 I, suppose this is equal A is missing, mu 0 I by 4 pi A here also A into 2 cancel, So, mu 0 I by 2 pi a. Thus, we notice that the magnetic field outside the conductor is inversely proportional to the distance. Magnetic field outside the conductor is inversely proportional to the distance from the axis of the conductor. If we plot the magnetic field along y axis and the distance along x axis, the nature of the curve is like rectangular hyperbola. That means with increasing distance the magnetic field is decreasing. Second application of Biot-Savart law, circular loop. Circular loop. We consider a circular loop of radius A, carrying a current I. We consider an elementary length dl. Due to the flow of current through the circular loop, we have to calculate the magnetic field at any axial point of the loop. Suppose P is the point on the axis. The distance of the point P from the origin O is equal to x. This is capital R. Now, according to Biot-Savart law, the magnetic field at point P due to the elementary conductor or elementary length dl is equal to dB mu 0 I by 4 pi dl cross r by r cube. The direction of magnetic field is perpendicular to the length as well as r. Suppose dB is the direction of magnetic field. This direction is perpendicular to r, that is this angle is 90 degree, also perpendicular to dl. If we take the elementary length dl, then the direction of magnetic field is like that. And if we consider the elementary length at this point, then the direction of magnetic field is like that. So, if we integrated this magnetic field or we calculate the magnetic field at point P due to the entire loop, then the dB describe a cone with OP as axis. dB describe a cone with OP as axis. Now, the component of dB perpendicular to the axis OP, is cancel out. Only the horizontal component or parallel to the axis is survive. So, total magnetic field at point P due to the entire loop B is equal to mu 0 I by 4 pi integration dl cross r by r cube. dl cross r by r cube. So dl cross r by r cube. So B parallel, only the parallel component of magnetic field is survive and the component of magnetic field perpendicular to the axis cancel out. So the parallel component of magnetic field is equal to mu 0 I by 4 pi integration dl cross r, dl cross r, dl r sin dB is equal to mu 0 I by 4 pi integration dl r into sin angle between dl and r. Angle between dl and r is 90 degree. 90 degree. Since r is the tangent on the loop, by r cube into parallel component that is sin theta. Or B parallel mu 0 I by 4 pi dl r by r cube into sin theta. R cancel, or B is equal to mu 0 I by 4 pi sin theta. Now from figure, sin theta is equal to A by R. So this is equal to A by R, or dl A by R cube. Now R is equal to root over A square plus x square. So total magnetic field on the axis due to the circular loop B is equal to mu 0 I by 4 pi into A dl by r cube. R cube is equal to A square plus x square to the power 3 by 2. Integration of dl is equal to 2 pi a, periphery of the circular loop, mu 0 I by 4 pi 2 pi a into A square plus x square to the power 3 by 2. 2 pi cancel into A mu 0 I A square by 2 A square plus x square to the power 3 by 2. So this field is produced due to the loop. So the magnetic field at the center of the loop is obtained by putting x equal to 0. So magnetic field at center is equal to mu 0 I by 2a. Thus, it is seen that the magnetic field at the center is maximum and the magnetic field is decreased with increasing the distance. Next we calculate the divergence of the magnetic field. Magnetic field. Divergence of the magnetic field. We know that according to Biot-Savart law, the magnetic field due to the volume current distribution of charge is equal to mu 0 I mu 0 by 4 pi J cross R by R cube into dV. Total magnetic field due to volume current distribution of charge is equal to mu 0 by 4 pi integration over volume J cross R by R cube into dV. Now take the divergence on both sides. Divergence of B, taking the divergence on both sides, mu 0 by 4 pi divergence of integration over volume J cross R by R cube into dV. Since the integration is taken over source point and the divergence is taken over field point, so divergence can be taken inside the integral, that is mu 0 by 4 pi integration over volume divergence of J cross R by R cube into dV. Now we have to calculate divergence of J cross R by R cube. Now divergence of J cross R by R cube is equal to, or can be written using the vector identity divergence of A cross B, divergence of A cross B, that is equal to B dot curl A minus A dot curl B, using the vector identity divergence of A cross B, that is equal to B dot curl A minus A dot curl B. We can write divergence of J cross R by R cube, that is B means R by R cube, R by R cube is equal to B and J is equal to A. So R by R cube into curl of J minus J dot curl of R by R cube. Since J is a function of x prime, y prime, z prime, J is a function of x prime, y prime, z prime, and curl is taken on the field point, that is function of x, y, z. So curl of J is equal to 0. This term is equal to 0. Now curl of R by R cube, curl of R by R cube curl of R by R cube can be simplified using the vector identity curl of phi a, that is equal to phi curl of A, phi curl of A plus grad phi cross A, cross A. Here phi is equal to 1 by r cube and A is equal to r. So this quantity is equal to phi means 1 by r cube curl of r plus grad 1 by r cube cross r. Since curl of r is equal to 0, so this term is equal to 0 and grad of 1 by r cube is equal to minus 3 r by r to the power 5 cross r. So r cross r is equal to 0, parallel vector of two identical vector, cross product of two identical vector is equal to 0, that is this term is equal to 0. So divergence of B is equal to 0. Divergence of B is equal to 0. This equation holds for all values of B produced by steady current or varying current. This equation known as Gauss law in magnetostatics. Gauss law in magnetostatics and imply that the magnetic monopole does not exist. Taking the volume integration on both sides, divergence of B dV, that is equal to 0, and volume integration can be converted into surface integration by Gauss divergence theorem. B n hat ds over surface, that is equal to 0. That means the magnetic line of force are always close, or magnetic line or magnetic monopole does not exist, or there are no isolated magnetic monopole. If you take the curl, similarly if we take the curl on the both side, we get the curl of B is equal to mu 0 j. This is known as differential form of Ampere circuital law. Similarly, if we take curl on both sides of magnetic field, then curl of B is equal to mu 0 j. This is the differential form of Ampere circuital law. You take the surface integration on both sides, curl of B ds over surface is mu 0 j ds. The surface integration can convert into line integration by Stokes theorem, that is closed integration over line C B dot dl is equal to mu 0 current density into surface, that is total current enclosed by the path, where I is the total current enclosed by the path. This is known as Ampere law. or Ampere circuital law. That is, the line integration of magnetic induction vector around any closed path is equal to mu 0 times the total current enclosed by the path. This is known as Ampere circuital law.